Okay, so for those of you that are at the breakpoint, did anyone find anything that's pointing at our shellcode or anything that we control or anything like that?
I think I have something which may be at a place we control. So it seems like the ESP plus 8 address is, at least for me, 12FFB0, which is within that buffer range.
Yeah, yeah, that's exactly right. So if we look at the stack, at the time the exception handler program starts running, at the point we gain control of EIP, the third address on the stack, 12FFB0, points to the current exception handler record. The first 4 bytes of the current exception handler record is that next pointer that we overwrote with this junk or whatever that didn't really care about it. It's just a pointer on a linked list. If we are to do something like jump ESP plus 8, we would be jumping to attacker-controlled data. Now, granted, it would only be 4 bytes of attacker-controlled data because what we have right here is 4017FF. This is what we use to gain control of EIP. The third thing on the stack here is a pointer to attacker-controlled data, AAAAA. But we can't clobber this because we need this in place to keep control of EIP, essentially. So what we could do is do something like jump ESP plus 8, and then put another relative jump right here, jump forward some bytes so that we're executing all this, and this is attacker-controlled data. And it turns out if this doesn't point to a stack address and instead points to like jump ESP plus 8 or something like that, the Windows exception handler will allow it. So I want you guys to, actually I'll just go ahead and tell you, I won't torture you too much. The general paradigm for what people use to exploit this is they point EIP at a pop-pop return instruction. Okay, so any sort of 2 pops followed by a return, because if we were to put EIP equal to one of those, when this runs, it would go pop this off the stack, pop this off the stack, and set EIP equal to this, and what's attacker-controlled data. Then what they do is jump forward past this, because we need this in place. This will be the address of our pop-pop return instruction. And in here, we can put our calc shellcode or whatever. So, who can find a pop-pop return style construct in the SCH overflow program? It's actually a very common construct. Let's see who can find one first. Pop into any 2 registers, it doesn't matter, then return. We just want to get rid of those 2 things off the stack. Have ESP pointing to here, return, ESP equals this, attacker controlled data, good to go.
E0.
What was it? 7C 901?
901 4E0.
Okay. This will actually not work if you use this one. So the reason is it's an exploit mitigation technology that I haven't talked about yet called Safe SEH. And what Safe SEH does is it registers a table of valid function pointers that a DLL is able to use as its exception handler. And if anything is not in that table, then the exception handler will not process it. So the pop-pop return isn't in there. However, a lot of modules don't opt into the safe SEH style table. It's on a per DLL basis. So there are going to be some DLLs and some components in your process that don't opt into safe SEH, that don't have one of these tables. And if the DLL doesn't have one of these tables, the process exception handler code is going to say, all right, it doesn't have a table, so just whatever, if the exception handler points in that DLL's address space and it doesn't have a table, then sure, just allow it because whatever, I don't care. So we can actually look at which modules opt into safe SEH and which ones don't with this cool plugin, which I'll talk more about tomorrow, called Gnarly. And as you can see here, Gnarly, written by Doc Savage here, has this cool ASCII art because any cool, respectable exploit developer has awesome ASCII art that he uses as a signature. And if we use .bang in mod, it tells us what has safe SEH on, what has safe SEH off, among other things like ASO. So in this case, all these Windows DLLs, like default Windows DLLs, like NTDLL, which I think is what you guys were referring to with that 7C one, have safe SEH on. So we can't point the exception handler function pointer into the NTDLL address space, just any bytecodes we want, because it has that table of valid exception handler function pointers.
How do you recognize that? From looking at the code? I mean, how did you recognize it when you saw that?
Which ones has safe SEH?
Yeah, when you looked at the disassembly, you recognized right away that it was the...
Well, I've got to reference that GTL.
Oh, the 7C and so forth?
Yeah.
Oh, it's just because I had that address range memorized, because I'm a giant nerd. So to use Gnarly, do .load Gnarly. And then if you use .bang in mod, it'll give you all this stuff, which we're going to use tomorrow to tear apart Windows exploit mitigations. And these two, I've compiled this binary specifically to not have safe SEH. So I was sort of expecting, Sam, that your issue was you accidentally turned safe SEH back on somehow. So if that says safe SEH on, that would be the source of your problems. But Windows is actually pretty good these days about turning all this crap on for their exploit mitigations. And so it's kind of hard to abuse the Windows ones, but most application DLLs don't opt into any of this stuff. So yeah, so like in particular, I just kind of randomly chose Flash, and guess what? You put Flash in Gnarly and it doesn't opt into anything. It has basically no exploit mitigations turned on. Not just Flash though, most application DLLs, like DLLs that come with applications not provided by Microsoft, don't opt into any of these things, so we can use pop-pop returns from their address space. In our case, I compiled it so that safe SEH was turned off in our SEH overflow, so anything that points in the text segment of SEH overflow should be fair game. So I think Zeno found a pop-pop return in there.
I've got 14014.
40, what was it?
1491.
Yeah. So this construct actually appears a lot, pop-pop return. And you can see, because it's really only like 3 bytes, 5B, 5B, C3, so just out of sheer randomness, those 3 bytes will probably appear somewhere in the code segment. But you could also use like add ESP8 and return or anything like that. That's just what the pop-pop return is effectively accomplished.
What's the best way to search for that?
Use a bunch of custom programs that I've written, to be honest. The way I usually search for it in WinDebug is that I know that pop ESI occurs right before return a lot, so I search for pop ESI and return. So I figure out what the opcodes are for pop ESI and return, and I do a search for that in a process address space. And then if I see one more pop for that, I know that I've got a pop return. And after a while, you can just sort of recognize that these are the bytes associated with pop. So forth. But there are some plugins out there that will kind of find it a lot more automatically. But it's really kind of like so common, you can probably just like scroll through the text segment in this assembly window and see it here. It used to be that EBX pointed directly at like attacker-controlled data, but this was like abused by the RPC decom code red worm or whatever, and so Microsoft felt compelled to change that, and so they made it where most of the registers are zeroed out when the exception handler begins running. Or not pointing to any sort of interesting data. But, the pointer to the exception handler record itself is still on the stack, 8 bytes up the stack, so they spent all that time and money to make it where EBX was null at this point, and not pointing at attacker controlled data, but hey, look, it's still 8 bytes up on the shell code, so it doesn't really accomplish much. We can still do whatever we want to with these things. Okay. So this is going to be the last lab of the day, guys. And it's going to be a little bit involved because there's some moving pieces in here that I haven't quite told you about. And I want you to get calc.exe to spawn an SVH overflow by making the exception handler function pointer point at that pop return. The pop return can either be in SVH overflow address space or in flash, because neither of those opt into offer that table of function pointers. You can just use the one that table of function pointers. You can just use the one that we just rattled off. That will get EIP equal to the first 4 bytes of the exception handler you've overwritten, and then you'll need to do some stuff to get calc.exe shellcode. That is your quest for the rest of the day. And then once you guys have mastered the art of overriding these exception handlers, tomorrow we will forge ahead with turning on all exploit mitigations and then redeveloping our exploit for this with all mitigations turned on so that you will be able to exploit vulnerabilities in the presence of all exploit mitigation technologies that Windows has to offer. So I'm going to start working through this on my own for anyone that wants to watch and follow along with me. So right here, well, first of all, what was the address of the... That's on purpose, so you know, antagonizing me, making fun of me for dropping the pointing stick all the time. What was the address of the pop return that you guys are using?
401.490.
Can you read it backwards?
Oh, sorry. 901440.
Okay, and then that should put pop return will make EIP point at where these bytes are at. So I'm going to do EP06 forward 6 bytes. Right here, I'm just going to replace this with a CC shellcode for now. Oopsie. Oh yeah. Oh, look at that. I'm sorry. 14. It was 90144000. Is that it? So at this point, I've replaced the exception handler function pointer with pop return address. That's going to point EIP at where these opcode bytes are at. So I'm going to change them to jump forward 6 bytes. Because that's going to go +1, +2, +3, +4, +5, +6, and give me these CC bytes. CC shellcode. And that's where I'm at right here. Now here's the problem. This is the limit of my stack, 130000. You can tell it's a bang tab extension. And I'm currently at 12FFB8. That only gives me 72 bytes for my shellcode, which isn't a lot in the Windows shellcode world. Windows shellcode is generally pretty beefy because all that crazy parsing and jumping around that I described before it has to do. So, what should we do? Dan, you have an answer? Yeah, how are we going to do that? So here's what I'm going to do. At this point, we know we don't have enough room. I'm going to put good old calc shellcode. I have no idea if this is going to work. We're going to run into that ESP corrupting us problem again. Right there, at the very beginning of my payload. Now, what was the address of my buffer? Was it this? Is that still valid? I don't know if it is or not. Let's see. B6. To FP16. Yeah, so this is where my buffer starts. This is where my shellcode will end up when I restart it. So I'm going to use the WinDbug on-the-fly assembly command to automatically calculate those offsets for me, like if they had the instructions to jump back to that address. So I'm going to do this. Okay. And that tells me what the bytes are to jump backwards to 12FP68. So I'm going to come here and replace my CC shellcode. With that, 9, KB, FB, FF, FF, which is just like jump a negative number backwards. And the single stuff there is going to start trying to execute deadbeat as instructions. Then I did that thing I told you guys not to do. I did a paste insert instead of a paste write. And the address of my The address of my buffer was wrong. I was using an old address. It's actually starting right here. So, dang, I gotta go back and change all that. So to recalculate that jump, I'm just going to go ahead and set the exception handler back to a CC break, or my shell code back to CC. Didn't need to do that. So I'm just going to frazzle. CC. All right, from here I need to calculate my jump back to this address. One weird thing with assembly mode is you have to prefix the addresses with 0x, like other things with WinDebug. So that's what I need my little small shellcode to be right here. So another important part of the payload you guys are developing, and the one that I showed, was that there was only one hard-coded address, which was the address of the pop-pop return instruction, which is very good in terms of reliability of exploits. The less hard-coded addresses you have, the better. And hard-coding the address of one pop-pop return isn't that bad, because with something like Flash, if you know the version of Flash that they're running, you can probably just query through the web browser interface, and it's easy to be like, all right, well, you're running that version, so I'll just have to use this pop-pop return address, and then bam, everything else is relative, and it's a super reliable exploit. That's right, Sam. The address we're returning to, we need to be at jump relative forward 6 bytes. So that pop-pop return will make EIP point at these instructions, these opcodes. And then EB06 will make EIP point to these opcodes. And these opcodes right here represent a jump backwards, or a shellcode here, because we don't have enough room on the stack to fit it in afterwards on this. And a lot of overflows, when you're talking about a real application, the stack is big enough, you can definitely fit the shellcode here. Not have to do all this, but this is just kind of like a proof of concept program. The stack doesn't have a lot of room, so you got to do that jump backwards. Any questions?
I'm working on that second jump. Is it just a jump to a specific address, or is there some way to relative jump backwards?
It's a relative jump, and you calculate it with the A command. So once you do this first jump, EB06, EIP will be pointing like right here. So So I'm going to make those CCs for now, so it triggers a software break when it hits them. And then you can figure out how to jump back to your shellcode by using the A command. So if you do A and then jump, let's assume my shellcode is at 12FB6C or something like that. I don't know, you'll have to look that up. It'll calculate it for you like so.